This video is all about standing waves, also called stationary waves. Stationary waves form when two waves are coincident and have the same wavelength and frequency. Here you can see on the screen an example of a standing wave. You will see that there is a blue wave moving from right to left, and there is a green wave moving from left to right. They have the same wavelength and they have the same frequency, which is why they are travelling at the same speed. The red wave is formed by adding the displacements of the blue and green wave together. And you'll see there are places where the displacements, when added up, always produce a resultant displacement in the same direction. And other places where, when the displacements are added together, the direction of the displacements are always in the opposite direction. In the position marked here, you can see that whenever the blue wave has a positive displacement, the green wave has a negative displacement, and of the same magnitude. So that point there always has cancellation between the two waves. It is a destructive interference. These positions are called nodes, so I've marked it here with an N. The resultant displacement at a node is always zero. Here you can see I've marked some more nodes, and at each node the red line never leaves the principal axis. The red line always has a displacement of zero. It is a position where there is always destructive interference. If you look at a position directly between two nodes, you will see that the displacement of the green and the displacement of the blue waves are always in the same direction. This is a point of constructive interference, and the red wave is the superposition of those green and blue waves. The displacement of the red line is changing as we go through time, but the amplitude of the red wave depends on the position between the two nodes. The biggest amplitude of the red wave is exactly between the two nodes, and the closer to each node you get, the smaller the amplitude. Remember that amplitude is the maximum displacement of a wave. So the amplitude of the red wave is zero at a node, and the point where the amplitude of the red wave is the maximum is referred to as an antinode. Antinodes lie exactly halfway between nodes. Here I've labelled the antinodes with a cross and the letter A. One wavelength is twice the distance between two adjacent nodes, or two adjacent antinodes. If we pick 2 points on the red line that are between two nodes, we can see whenever one of those points is moving down, so is the other. And whenever one of those points is moving up, so is the other. So those 2 points have a 0-degree phase difference. If, however, we pick 2 points on the red line with a node in between them, then we can see that whenever one of the points on the left is going up, the point on the right is going down, and vice versa. So those 2 points have a 180-degree phase difference. In fact, as long as there is an even number of nodes between 2 points on a stationary wave, you will have a 0-degree phase difference. And as long as there is an odd number of nodes between 2 points on a stationary wave, then there will be a 180-degree phase difference between them. In order for a stationary wave to form on a string, there has to be a length of string equal to half of an integer multiple of a wavelength. The shortest length of string that can form a stationary wave is one that is half of a wavelength long. This is called the first harmonic, or the 0th overtone, which is shown here on the top left. On the top right you can see the first overtone, or the second harmonic, and in that case the length of the string is equal to 1 wavelength. And we keep adding half a wavelength onto the length of the string to get the higher harmonics. On the bottom right you can see the 6th harmonic. Stationary waves simply cannot form if the length of the string and the wavelength are incompatible. It's very important to remember that the length of the string has to be half an integer multiple of the wavelength. When answering questions about stationary waves in pipes, where there is no string with a node on each side, it is essential to draw a diagram. If the pipe is open at one side and closed at the other, then we know there'll be a node at one side and it's open at the other. And then your diagram would have an antinode at the open side, curving from an antinode down to a node and back up to an antinode. And that would be the wave that can fit. And the distance between the top and bottom of this pipe would have to be, in this case for the first harmonic, 1/4 of a wavelength. Similar to before, you keep adding half a wavelength on to make the different harmonics. And every additional harmonic has an additional node within a stationary wave. So my top tip for stationary wave questions is always draw a diagram, do not be afraid to sketch things, and these sorts of questions tend to be about geometry, not memorizing formulas.